It is time to evaluate our parse tree. Parsing is fun, but our language does not come alive until we actually evaluate it. Evaluation is what separates what we write from a bunch of meaningless symbols to something that conveys meaning and has boundless potential. There are several strategies to evaluating the parse tree that we have created. The simplest way is to simply walk the tree, visiting each node and doing whatever the node represents. The strategy is called tree walking and is the archetype of interpreters. There are variations on tree walking to optimize things. Instead of interpreting the AST directly, some languages convert it to bytecode, which can then execute on a virtual machine. On other occasions, the AST is skipped completely and the parser instead emits bytecode. After this bytecode is produced, instead of being executed on the VM, it can also be converted to native machine code by the VM just before it is executed. This is what you will hear be called a just-in-time compiler. Another common optimization is for the AST to be walked, but to make optimizations, such as removing unused variables, optimizing loops, etc. Bytecode, virtual machines, and even small optimizations can make evaluating a complicated process. We are going to take the path of least resistance and just create a simple tree walking interpreter. However, this is nothing to scoff at, and it is actually how most languages begin. Ruby, JavaScript Core, Lua, and Lisp are just some examples that started out as simple tree walking interpreters and later transitioned to much more optimized and complicated evaluation strategies. Tree walking is the easiest way to get started, the easiest to understand, and easiest to extend later on. The only things that we need are an evaluator function and a way to represent the values of our language in the host language Go. The evaluator function itself doesn't tend to be too complex. A snippet of its pseudocode could look something like this. You'll notice that it is recursive in nature, and in this scenario we are evaluating the left and right children separately with calls to evaluate, and then we evaluate the current node operator. The question to answer is, what will this evaluate function return? What do the values of left and right look like? We are going to start with a base object interface. Concrete implementations will contain booleans, integers, etc. into this base interface. So create a class called object.go and create the object interface. Then, like our token type, define an object type to help us differentiate between the different types we will add to our language. Give the interface a type method that will return an object type and an inspect method that will return a string. Currently, the only types we have in our language are integers, booleans, and a null value. Let's create each of these classes. First, define an integer object type in the object package we just created. Next, create an integer.go class that will implement our object interface. The only member of this class is a 64-bit integer, which we will call value. We also override the inspect method, and all we are going to do is print the value of our integer. Next, override the type method and return the integer object type we just created. When we parse, we create an integer literal AST node. Then, when we evaluate, we will turn that into an object integer and then pass this reference to it whenever we need its value. Now let's do the same thing for boolean. Add the boolean object type to the object package. Next, create a boolean class that looks almost identical to the integer class, the only difference being that the value field contains a boolean and the type returns the new boolean object type. And in the inspect method, the format of the printed statement is T instead of D. Now, if you are so inclined, you can add the explosive and dangerous null type to our language, and our process will be identical. Add the null object type and the null class. The null class is unique as it has no member fields. And with that, we end the video. In the next one, we will be writing our eval function. See you there.